start. It's fine.
Welcome back. Very pleased to introduce Gunnar Carlson, who's going to be telling us about the shape of data in the first of our lectures on applied algebraic topology.
Great, thanks very much. One of the things I noticed about a year or so ago, I was walking through San Francisco airport, and I looked up and I saw a billboard hanging from the ceiling, and the billboard said, "Big data meets the cloud." And it was an ad for a company that was doing data storage. Now, what that told me was, they're talking about big data or data, which is a mathematical or an engineering problem, but it's really gotten everyone's interest to the point where you're putting up billboards at San Francisco airport on it. So that idea, the idea that understanding big and complex data is something that's of importance to a lot of people, was motivation for the project that I'm going to be telling you about over the next 2 or 3 lectures. So let's jump in here. So I want to make a couple of statements first, and then I'll sort of back them up or show you what I mean by them. First one is that data has shape. Shape for us is something that we think of, well, we topologists, of course, think of it in higher dimensions. Most people think of it in 2 or 3 dimensions. Typically, what a shape is a geometric object, maybe given in terms of a distance function, in terms of a metric. It might be given in other ways as well. Anyway, I want to argue that data has shape in many cases, most cases, and also that the shape matters. That the shape of the data is something that you want to understand if you want to understand your data, if you want to draw information and even knowledge out of what is just a bunch of bits in terms of the data. Okay, so what do we mean by this? Here's a real simple example. So if you look on the left there, this is a data set that one might see. So I'm showing you 2-dimensional data sets here just because I want to be clear about that we can see them and so on. Most data sets will be much higher dimensional than that. But imagine that this is a collection of points in the plane, data points given with 2 different coordinates. And I think you would agree that if we look on the left-hand side over there, you'll see that the data seems to break up into 4 conceptually distinct groups. Now, so what that says is, that, probably if we filled this in, this is sampled now, if we filled this in, we'd have 4 connected components in our geometric object that we are sampling from. Okay? So what I would say is the very first, the most primitive aspect of shape is certainly the number of connected components that you break into. It's the first thing you ever do, and once you do it, you've done it once and for all, and you then study the individual pieces separately. So it's a very important, but very primary aspect of shape. And people who study data have developed algorithms, many different algorithms, for basically deciding how a data set should be broken into clusters. And clusters here means disjoint pieces that are sort of far apart from each other. Typically, they will involve then, the groups will be conceptually distinct, and we'll talk about different phenomena. So you might think here about supposing that we had data from diabetes patients where we know that there are 2 distinct groups. There's a type 1, which is a juvenile onset, which is a different disease from the one which is adult onset, type 2, which can be treated usually by lifestyle changes. So in any case, clusters is a very important aspect of shape. Here's another one. The state of Michigan breaks up into 2 connected components, and so you need the bridge or a ferry or something to get across. You know you would need that. Now here's an interesting one, and this isn't real data, by the way. When I talk to biologists about this, and I put this up as data from real life, they laugh at me because this is coming out of simulations of Lotka-Volterra differential equations that you've probably seen in calculus texts. They are sort of, they're an interesting proxy for reality. But the point here is, so actually I'm showing you several data sets here. Each one of those colored loops there is with a different set of parameter values in the differential equation. But the thing I want to point to here is the fact that these sets don't break up into clusters at all. However, they're all loops. And what that loopiness here, what that loopiness reflects is the fact that there's periodic or recurrent behavior going on in this data. Because what happens with this data is, at a certain point, maybe there are lots of predators and very few prey. And at that point, the predators start to die off because there's not enough for them to eat. The prey starts to grow in population until you get to a point where there are a few predators and lots of prey. And at that point, the predators start to feast again. And anyway, it goes around in a periodic or a recurrent fashion. Okay? So the shape of the data, in this case, being a loop, is reflecting the fact that there's periodic behavior going on. Here's another one. This is some astronomical data. I won't bother you with the details about it, but I just wanted to give you another indication of what we might mean by shape. See, here, look at this data. You can see that there is kind of a central core there in the middle at the bottom, and then there are 3 different flares, we might call them, going out from that central core. Okay? So this looks kind of like a letter Y or an upside-down letter T, if you like. And its shape, then, is of interest because one thing this might reflect is the fact that in the central core, that's kind of the normal stuff that happens. And then the different flares are the extremes, the different extremes that can happen, the ways things might go off the rails, for example. Okay. Now, so now having made that observation that the shape of the data is, can be important in interpreting it, now we say, well, what's this part of mathematics which deals with shape? And of course, we all know the answer. Topology is essentially a formalism for measuring and representing shape. Those are 2 different themes in the subject. As you know, it's been in pure mathematics since Euler in the 1700s. What's been happening, and what I'm going to be talking about today, is the fact that what's been happening in the last 10 or 15 years is people have been saying, look, it's great to do topology on sort of complete spaces where you have them well defined by systems of equations or simplicial complexes or whatever. But wouldn't it be great if we could extend those methods to what I would call point clouds, which are just sampled versions, finite sets of points, but which are like the ones that I just showed you? Is there a way of doing all the things topologists like to do, but for point clouds instead of for completely well-defined spaces? That was Euler's thing. So 3 ideas. I think you would agree with me that all these are fundamental ideas in topology. One is that we as topologists study shapes and geometries in a way which is not dependent on the coordinate system. Right? In fact, we do even more. We actually are going to say we're invariance under deformation. That is to say, that if you have a geometric object, we like to be able to stretch it and compress it and so on and still have the properties remain the same. And then a third thing, and this is this kind of a second theme within topology, I would say, is the fact that topology also produces compressed representations of spaces. So think of triangulations here. Where you have an infinite object and you're replacing it by some finite list of simplices. Again, pictures to illustrate this, I think not so important for this audience. Circle obviously can be seen in many different ways. It can be sit at an angle in 3 space. Okay. So here's, I'm going to try not to grind too many axes today, but I want to grind one axe here. This is the invariance to deformation. And what I would argue is that's a fundamental property of the human visual system. The human visual system is very easily able to track and understand the fact that one object is gotten from another one by a deformation. So if you look here, it's responsible for the fact that we can recognize a letter A no matter what font it's in, no matter if it's maybe drawn on the round surface of a soccer ball or if it's seen at some funny angle. We can always recognize it, and we recognize it instantly because the A is the one with the loop and 2 legs, right? And the B, on the other hand, is the one with 2 loops and no legs, and we can see the difference. Now, so when I talk about topology, that's the example I like to give. The example that we often have given in the past is the one that says, deformation invariance. Coffee cup is the same as a donut. Coffee cup, you can deform the coffee cup and you can get it into the shape of a donut. isn't that a huge case of shooting yourself in the foot when you go and tell people, we are the people who can't tell the difference between a coffee cup and a donut? Instead of making a positive statement and saying, look, what we can do is, we can do this, topology is exactly the stuff that does this kind of robustness that captures the shapes and so forth. Okay, here's a sort of a more data-centric version. Suppose that you had an ordinary, one of the things that people who handle data love to do is to sort of change coordinates and get it in a way that they think it sort of shows up some phenomena more clearly than others. One particular way of doing that is a log-log plot, where you just replace every coordinate by its logarithm. And this is what happens when you do this to a circle. The circle that's sitting somewhere up in the first quadrant. And so you see here that what you get, of course, you get a round gadget, but it's no longer a round circle. It's instead, it's a loop. So from the point of view of data analysis, you would like to understand some properties or measure some properties that don't change with respect to these coordinate changes or deformations. And finally, the compressed representations of geometry here. Look, a circle is infinitely many points and infinitely many pairwise distances. That's very hard to store in a computer. On the other hand, if you're willing to sacrifice a little bit of the, of the roundness of the circle, a little bit of the curvature information, you can keep and reconstruct the circle very easily with 6 points and 6 edges, okay, which fits in a single byte. All right, so I would argue that topology has two tasks, measuring shape and representing shape. And in fact, that fits very nicely if you think of the themes and the subject in the 20th century. Basically, there's a lot of work done on homology, which is what I would call measuring shape, somehow getting invariants that capture shape. But then there's a second aspect, which is a little bit more geometric topology, where people have asked questions about, which spaces can be triangulated, and can be triangulated how? What kind of representations can we get for them? Both those are important, and they're both going to be important in the applied stuff that I'm going to be talking about today and Monday. All right, so now here, I think this is just a summary. We all know this about Betti numbers, and you all know this very much as well. Just remind you of this one. This is mod 2 homology for the Klein Bottle. I'm sure you're aware of it, but maybe make note of it we're going to look at one a little bit later. All right, so what are the salient properties of Betti numbers and homology? Betti numbers are dimensions of Boolean vector spaces, hk of x. This was this wasn't understood in the early part of the 20th century. People were trying to count torsion coefficients, as they said, and Betti numbers being ranks of things. But they didn't really recognize that they were dimensions of vector spaces, nor would they have understood what the value of that was. Okay? But the value of that is, and that was Emmy Noether's huge contribution, was to recognize that everything becomes simpler when you make the definition a little bit more abstract. And say, look, I'm going to study vector spaces or abelian groups as my objects, not just the numbers attached to them. And when I do that, what it buys me is I can now say these vector spaces depend in a functorial fashion on the space. And so not only do I get numbers, I get vector spaces, and I get linear transformations between vector spaces. Okay, and so here we have these constructors which will construct complexes from spaces and then ultimately do linear algebra on them to compute homology. All right, so here's what I would argue in terms of starting to think about this for the use in data. Homology gives signatures which are kind of signals for different kinds of features. Loops, two-dimensional surfaces in your space, and so on. The complexes that are built, if they're small, can also be used as combinatorial and compressed ways of representing shape. The Eilenberg construction, of course, is hugely infinite, is not computational at all, but there are many smaller versions exist when you have additional information about your space. Okay. All right, so now let me, so I just argued that, topology is about studying shape. Now, there's a real, the simplest aspect, or one simple example of shapes, of course, is the letters, as I was talking about. So we talk about the letter A, B, C. Okay? And suppose I computed homology here. I would distinguish between all three of these letters. This one has a Betti 1 of 1, Betti 1 equals 2, and Betti 1 equals 0. So I get very optimistic, but as soon as I go any further, I lose. Right? I only have three classes of letters as far as the Betti numbers go. So here, for example, D, Betti 1 equals 1. D would be the same as an A. And so someone criticizing the application of topology in this setting would say, yeah, you capture some things, but gee, it isn't really a very strong detecting device for shape, is it? Okay? And so what that means is that we have to be prepared. So we need varying versions of homology. Ones that are built toward detecting certain kinds of phenomena. So I'll give you one example. So there's a notion of so-called Borel-Moore homology. And it's dual, by the way, to cohomology with compact supports. Okay? This is interesting when it's applied to non-compact spaces. These theories have been extensively applied in the study of non-compact manifolds. And what it is, the Borel-Moore homology captures the inverse limit, roughly speaking, of x mod x minus k, where k is a compact subset. And so the effect of Borel-Moore homology, then, it turns out, is, I want to leave this open. Let me come over here. Borel-Moore homology, for example, sees if I have this kind of situation where I have infinities out at the ends, Borel-Moore homology will capture this. It'll say Borel-Moore Borel-Moore 1 is equal to, k squared if k is your ground field. It's really the homology of the one-point compactification, if you like. Okay? Now, so it sees this. So notice this space, as I've written it, is contractible. Okay? But Borel-Moore homology has nevertheless captured the distinction of that space from a point. And similarly, Borel-Moore of Rn equals k for star equals n. So it's a much more refined detecting device for shape. You have lost something in Borel-Moore. You have lost the functoriality, because Borel-Moore is functorial only for proper maps and is homotopy invariant only for proper homotopies. But what you've done is you've said, look, now I can measure something about the ends of the space. So at this point, now you see, I see the difference between an A and a D. Because if I can interpret these things down here as ends somehow, what I will see is that although the homology of these two is different, the Borel-Moore homology of these things as ends, this will look like that, and the D will still look like that. So even just introducing this Borel-Moore gives you a lot more discriminatory capability for shapes. And then there are other things you can do. You can then actually build kind of tangent complexes of spaces and recognize distinctions between those. So for example, if you have an X junction here, you can actually build a complex in a natural way which sort of breaks it up into its two pieces, blows this up. Okay? So in any case, my point is just homology is a powerful tool. We want to be flexible in applying it and in how we modify it so as to capture things that we're interested in capturing. Okay. All right, so now let me get down to the heart of the matter here. So what I want to do, having said that we're going to want to do homology in all different kinds of contexts, I want to extend homology to this setting that includes point clouds. And by the way, for point clouds, we'll just mean finite metric spaces. Okay? Most data comes equipped with notions of distance. If they're high-dimensional tabular data, it could be ordinary Euclidean distance, or angle distance is another possibility. Other data comes as sequences in an alphabet. That comes up in biology a lot. And at that point, you might measure it by some different notion of distance, which would be, for example, a Hamming distance, which counts the number of places at which the two sequences differ. OK, so now we're going to try to talk about persistent homology. So the question is, how do we measure the shape of data? How do we build homology out of data? After all, the finite sets are discrete. These are discrete topologically. How do we get any kind of information about shape from them? So it turns out that statisticians actually knew what the idea should be a long time ago. Okay? They were interested in understanding the very first question I wrote down, which was the zero-dimensional part. That's how many connected components does a space break into? And so what statisticians did was this. They said, and let me draw this here. Let's do the following. So suppose so X is a finite metric space. And so now I'll define an equivalence relation. Twiddle R on X is defined by, well, X and X twiddle R X prime, if and only if the distance, this is equal to the equivalence relation generated by. Right? So in other words, I can think of it as just drawing edges, if I have them laid out in the plane or whatever, draw edges between the points whenever the distance is less than r, and then just do the connected components of that. So what that does is, so X mod twiddle R is a quotient. It's a set that statisticians would call clusters. It's a set for each R. But here's a key observation. Note that if R is less than R prime, then X mod twiddle R maps to X mod twiddle R prime. Because twiddle R prime is a coarser equivalence relation than twiddle R. And so what you have is not only a bunch of sets, one for every value R, but you have maps between them, a diagram like this. So the statisticians they had gotten to this point. They said, look, we have this possibility of building these equivalence relations. And they said, but how do we choose R? Right? They went through, how are we going to choose R? And so they built a lot of interesting kind of ad hoc methods for doing it. All of them break at any, and don't give useful answers. And so the insight here was to say, actually, we don't need to choose the threshold. We can represent this whole diagram by a single simple object called a dendrogram. Okay? So the dendrogram here, the way to understand it is to see that the data points here are all lying along that the line here. And now, at every level, you can tell how many clusters there are and which points belong to which cluster. Because look up at, say, point 8. If I go across at point 8, what I see is I've actually got two clusters, including the green and the red on the left and the purple and the green on the right. If I'm going at point 6, I instead have 4 clusters. The green, the red, the purple, and the green or grayish there. But I have more. I have the maps between them. So I have the whole diagram of sets. Okay? And that was their observation. So that has turned out to be fantastically useful. Okay. Okay. Now, but we don't want to just understand connected components. We would like to do something similar to try to understand, say, loops in a data set. Okay. So we could do this. We could use the nerve of the covering by balls of a given radius, or we could use the exact analog of what the statisticians were doing here. So let's do the following. Let's notice that if I build something called the Vietoris-Rips complex, this is for a metric space X here. So the vertex set is X, and X naught through XK spans a K-simplex if the distances are all pairwise. Okay. I can build, this is a simplicial complex. It's an easy observation that what the statisticians did over here is just take pi naught of VR of x and r. So the statisticians took pi naught. So, but what we're saying is we could build the geometry. We build a whole space here. And not only that, the spaces fit together. So here's a space that one could build. This is 6 points. But the more relevant picture is this one, where we've just got 4 points. And now there's a threshold. The threshold down here says, 4 points. Nothing is connected. In the middle, as I've increased the threshold a bit, there are some overlaps. At that point, I will get the square, the 4 points, and so there's a loop there. And then, of course, as I increase the threshold even more, I will get something which is a full tetrahedron where we've lost the loop, we've lost everything, it's all contractible again. Again, the key observation is the functoriality. Just like over here on the set of components, in this case, the complexes map to each other, right? As I increase the threshold, I will get maps of spaces. And so what that means is I have an increasing sequence of simplicial complexes. I'm now free to apply not just Betti naught or H naught, but Hi for higher values of I. And so what I get, and I'm doing homology with field coefficients here, what I get is I get a diagram of vector spaces. So here, I showed you all sort of continuous values of R here. For simplicity, I'm going to consider discrete values. So think of some very small number epsilon and just take all the multiples of those epsilons. So I'm going to consider only those. And so what I will get then now is a diagram of vector spaces. Just like we have a diagram of sets over here. Okay. And so what we're going to do is we're going to say, look, this is what you get when you apply homology to a point cloud. You don't just get a single vector space, you get a diagram of this shape. So we're going to give a name to those, call them persistent vector spaces. Now, of course, vector spaces we classify by their dimension. The question is there a classification of persistence vector spaces up to isomorphism? Is there an understandable such classification? So it turns out, and let me see, where's the eraser here, that there's a very simple little transformation that you can do. So we can talk about the category of persistence vector spaces. So things, diagrams of this shape. But here's something I can do with a diagram like that. I can transform it into V naught plus V1. Take all of them together. That's still a K vector space. But now there's a shift operation. Because of the diagram structure, there's a shift operation. So let's call all these sigma. So a vector V1, now so action by t, say. So t is a variable. So t times V naught, V1, and so forth is equal to 0 V naught, sigma V naught. Okay? So what this is, I have now given you a K vector space structure and also given you an action of a generator T. So when you trace all this out, it turns out that this category of persistence vector spaces is equivalent to the category of graded K of T modules. Now, K of T, a polynomial ring over a field, is a principal ideal domain. In fact, this one is graded, so it's actually a graded PID, which is an even simpler object to understand. Yes?
Are these persistence sequences? Are
They are. That's right. So all a persistence vector space is, it's a, a parameterized family of vector spaces with linear transformations going from one to its neighbor on its right. Okay, so this fact says that we certainly know that there's a complete classification of modules over a PID. Okay. The way it turns out, remember, there's some free terms, and then there are some torsion terms, which can be written as Z mod, or your PID mod, a power of a prime polynomial or of a prime element. In this graded case, it's even simpler. The modules look like this. The modules can either have a starting point R and then go off to infinity. That's something we might write as K of t shifted by R. Okay, because it's a graded module, so it's got a placement. And then there's also, though, this R to R plus S, like this, which is K of t mod t to the s of R. Okay. Those are the only indecomposables that occur within these modules. And the theorem is that everything can be written as a direct sum of such indecomposables. So what that does is it gives us a classification for these persistence vector spaces analogous to the one that we have for ordinary vector spaces. So, and so the upshot of that is, and here's the algebra, but the picture is this. See, let me just say, notice each of these modules, each of these irreducible modules, indecomposable modules, can be thought of as an interval. In one case, it's actually infinite out on the right, but these would be finite intervals, and so they might be specified by their left and right-hand endpoints. Okay? Yes?
So when you said that you're going to consider finite vector spaces, what are you sweeping under the rug? Do you really want to only look at the vector spaces as the persistence sets change, or is it like maybe really should be like a topological?
Well, wait, actually, are you asking the question? So here was the thing I was concerned about. That I wanted to, in other words, originally I gave you a persistence gadget as parameterized by all real numbers. Okay. Now I'm saying I want to do this just for the integer values, say, okay, because I get a good classification this way. Now it turns out actually that you can actually do the algebra for the whole continuous classification, but it sort of takes you, it gets you into some non-Noetherian rings. Ultimately, they're coherent, and it works out well that you can get the same classification there. I just didn't want to take us down that algebraic road. Yeah. And for practical purposes, if you choose your, the gap, very small, there's no actual difference.
Right, but the question is, of course, like what would you choose as epsilon? That was the whole question.
Sure. So, that, of course, would be, you might choose something like, 1,000th, or some number less than the smallest non-trivial interpoint distance, for example, would be one heuristic that one could use.
Well, but the question is, what are the morphisms? Because if you choose a different epsilon, then
Oh yeah, no, I fix I have to fix one epsilon. If I'm going to discretize like this, then I fix one epsilon and I stick with that. And so the morphisms are simply the morphisms, preserving, taking V1 to V1 and so forth. Okay. So this is one of these barcodes laid out like this. The vertical aspect of it has no meaning here. That's just to look at them. We're considering a set of intervals, and I've just laid them out so you can see the different intervals. But notice what we're seeing here is we're seeing a small number of intervals of short intervals here on the left, but then one much longer interval. And that longer interval is the signal for the presence of the big loop over there, and then these smaller ones are the little loops that are happening as the Vietoris-Rips complex is arranging itself for small values of the parameter. Okay. Okay. And let me just give you one other version of this. Here's another data set, slightly larger, more realistic data set. I think you would agree with me, that if we look at this complex, the answer we'd want to get out is Betti 1 equals 1. Right? But as I've built the complex here, if I go to compute the homology, I will have Betti 1 is computed as 3, right? Because of the fact that, yes, I have my large loop, but then I have the two smaller ones, which come presumably from some failure of sampling or whatever, and there's the sampling hasn't been done finely enough. And I can't tell the difference between those. In other words, that is to say, I can't if I'm a computer. If I'm a computer, I simply do my linear algebra and I get the three of them. Now, you might say to me, oh, but you just chose your threshold wrong. Okay, so let's increase the threshold. Now what happens? Now I fill in those two upper blobs, so that's a good thing. The bad thing is that I introduced another edge down here. And so, that it looks like I can't win, right? No matter how I choose my threshold, I lose, right? I get the wrong answer. The answer, though, is that it's not about any individual place. The answer is that the geometric structure here is about those things which persist across changes of scale. So which features, which elements here persist across the changes of scale? Well, the two little loops die across the change of scale. The big one persists. And then as I go to this one over here, the big one came from below. The bottom one exists there, but it didn't come from below. So the only one that's persistent is the big one. So that is how you characterize the sort of the larger features, or the ones that we might think of as actually coming from the geometry of the underlying space. Okay. So what I want to show you now is how this whole business actually plays out for a real data set. So think about the following. Suppose that you're going out and taking pictures with a black and white digital camera. Each such picture can be viewed as a vector with one grayscale coordinate for every pixel. So, but most cameras, all cameras, have lots and lots of pixels. So this becomes a very, very high-dimensional space in which these images lie. Okay, we'll call it pixel space. So David Mumford asked the following question. He said, within this set, imagine just as a thought experiment that we went out and took every single picture that could be taken in the world. Every possible angle, whatever. If I took all those images, that would produce some set within this very big pixel space. And, Mumford asked, what happens? What can we say about it? Okay. Well, let me say, the sort of answer that a topologist might want, that you or I might want as well. The pixel space is 10,000 dimensions, and the codimension is 3,048. So we have a manifold of dimension 6,000 something. That would be an interesting answer, but it's not very likely that occurs. I is very high dimensional, so that's certainly true. I is also very sparse in P, because actually it's very hard. There are a lot of conditions, as you can tell. If you start to write down at random draw an image by simply assigning grayscale values arbitrarily to the entries, you'll never get anything that looks like an image. So, what the result of this thought experiment was sort of negative in a sense, that the direct study of I will be very difficult. We don't really expect to be able to understand I directly. But their point was, let's do something a little more, a little different. Let's study the statistics of not the whole image, but of the 3x3 patches within this image, within an image. So we're going to study these 3x3 patches. Now we're looking at something which is not sitting in thousands of dimensions. It's sitting in 9 dimensions. It's a little high to visualize maybe, but it's not at all out of the question among the things that topologists do. Okay. So what happens initially now? Each patch like this gives a vector in R9. Next observation, though, is the following. It says, look, most patches, most images have some solid patches in them. Each such solid patch is going to contribute a ton of constant 3x3 patches. So that for most images, those constant or near constant patches are going to dominate the statistics. Okay? So it's a useful observation to make, but once we've made it, the strategy should be, all right, let's ignore the part that's constant and study the rest of it, where something is changing. So we're going to remove these low contrast images, or nearly constant ones, as not interesting, and study only high contrast patches. And that's what Mumford and company did. They built a database of high contrast patches, about 4.5 million of them, coming out of a database of 5,000 or so images taken by some Dutch neuroscientists in Groningen and Holland, driving around town and out in the countryside. Okay. Okay. All right. So now we have some high contrast patches. We have a database of things where something is actually changing within the 3x3 patch. Okay. First step that they do is to normalize the mean intensity. So we have a data set of 9 entries. There's a mean value of those. You can mean center it so that the mean is actually 0. That is to say, you subtract a certain constant value from them until you get the sum of all the entries being equal to 0. Okay? Well, the effect of that is taking you off a 9-dimensional space and putting you on an 8-dimensional hyperplane. Okay? And what this means is essentially, we're going to, if I have 2 patches, if I can get from the one to the other by just changing the brightness, I consider them the same. And this is sort of, the philosophy here is, by the way, to try to understand the structures of images that occur, not exact absolute levels of intensity. We can also now normalize contrast because we removed all these nearly constant patches, which means that when I go into the 8-dimensional space, I can remove a little ball around the origin. And so I'm now able to divide by the L2 norm. And so I now obtain data that lies on a 7D ellipsoid here, actually. So, so I have a data set sitting on S7. Okay? And again, this says we also are not interested in absolute values of contrast. In other words, if I turn a contrast knob on a patch, I want to consider those two as the same. Okay? So now we have a set of point cloud data lying on this sphere, or ellipsoid, in R8. And so now, so this was a data set that they constructed and studied. David actually lectured about it here at MSRI about 10 years ago, and that's kind of where we heard about this data set. It seemed like a very natural place to first test persistent homology as a way of finding qualitative structure in data sets. Okay, but now here's what happens. First observation. Actually, if you go into the 7 sphere, no matter where you go in that 7 sphere, you're not very far from a point. So in a sense, the point cloud fills out the 7 sphere. Now, so we could go ahead and maybe attempt to compute the persistent homology, and at the end of the day come out with the homology of the 7 sphere then, because it fills it out. But of course, it would be kind of like running around in circles. We placed it on the 7 sphere after all, and so if all we're seeing is that it fills it out, it's not so interesting. Okay. Turns out, though, that the density of the points varies a great deal. Okay. So there are certain regions where there are many patches in that region, and others where there are very few, where they're very sparse. Okay. And so the idea is we're going to try to study the high density patches among the high variance patches. Okay. Now, here's the thing. When we talk about density estimation is a very highly developed subject within statistics. And one can talk a lot about it. Here we need something very crude only. The only thing I want to point out is that oftentimes they come with a parameter. So one strategy for estimating density, for example, is fixing a radius r and saying, now tell me how many points are in a ball of radius r about my point. If that number is big, that's a higher density as measured by this thing with parameter r. If it's small, that's a more sparse situation. Okay? But changing that parameter, gives me a different value of density. In other words, if I'm choosing a small ball and counting the number of things in a small ball, that's different from counting it in a large ball. So those are the two different ones we're going to look at. Okay, so here's what happens. We sample down 50,000 points. And this is choosing a large ball, if you like. So this is a density estimator which essentially estimates density by counting number of points in a large ball. And this is a Betti 1 barcode. So I think if you look at it here, what you can see happens is you've got a lot of little short lines on the left and then a single long bar. So this is very similar to the schematic barcode that I drew for you under that original statistical circle. Now this suggests, a long line suggests that we've got something which is Betti 1. So we're going to try to explain the Betti 1 equals 1. And the one principle that one can use in trying to explain anything is called Occam's razor, which says, you choose first, the first thing to check is that which is the simplest hypothesis which would explain, the finding. So in this case, Betti 1 equals 1, the simplest space with Betti 1 equals 1 is, of course, the circle. Okay, so is this set clustered around a circle? Okay. And it turns out it is, and for a very simple, straightforward reason. If you look at this, this is what I would call the primary circle. And it lists the patches going around there. And so what you can see is that this is simply a discretized version of a linear gradient going from light to dark, but at different angles going around. And so the reason there's a circle here is because there's an angular component to it. And so that's what you see. Okay? Now, what we had thought was, yes, okay, this is nice. Maybe we should at least verify that it always works this way no matter which density estimator I choose. In other words, supposing I choose a density estimator for smaller balls. What happens then? We certainly expected to see the same result. But this, in fact, is what comes out. So this is what I would call the more localized density estimator, a smaller ball. And it comes out no matter how you sample your 50,000 points. And furthermore, it's very consistent. It's not that there's a bunch of long lines. It's that there are 5. You always get 5. Okay, so that's something more interesting you can try to explain. You can try to approach this with Occam's razor, but it's not so easy anymore because it's not clear what's the simplest space with Betti 1 equals 5. So after scratching our heads for a while, came up with this. This is one version. So this is, we call this the 3-circle model. So that black circle up there is the same circle that I just showed you. It's the one that consists of the linear gradients. Okay? Now there are 2 secondary circles. And here, because of the fact that I've had to project this into 2 dimensions, it's not clear from the picture, but the idea is that the 2 circles, the red and the green circle, both intersect the black circle in 2 points, but they don't touch each other. Okay? It's a little awkward to make that happen in 2 and 3 dimensions, but after all, this thing sits most naturally up in 8 dimensions. Right? And where it's very symmetric and nice. So this is one example, and here's the picture that shows you that Betti 1 equals 5. We are, of course, allowed to sort of move the edges around as much as we want. You can see here that there are 5 loops, Betti 1 equals 5. So if the data fit with this picture, that would be a satisfactory answer. It would be, we would have been guided by the homology to this picture. So the question is, does the data fit with this model? And so the answer is that actually it does. It fits beautifully with this model. So here's one of those secondary circles. So now what we're looking at, you can see that there's not an angular change happening. Instead, what's happening is, if you look at the top there, I see that's a primary circle patch. That's a linear gradient up there. But now what's happening as I move to the right is the far right-hand bar is kind of getting grayer, and the middle bar is going to turn white. And then at a certain point, I get to this dark region with a white line in the middle of it. Okay? And then this other one grays out, and then I proceed in the opposite way on the other side. Okay? So these patches turn out to be what happened. And the way that you find this out, of course, is you actually go back into the data, into these dense data points, and you find out, you look at them, and you see that these are the new ones that occurred beyond the primary circle. So what's nice here is then that now there's kind of a picture here which says I've got the two secondary circles, and you can see that the secondary circles, two parts of them match up to two parts of the primary circle, but they don't touch each other because, well, the one consists of vertical and the one consists of horizontal. Okay. All right. But now the question is, suppose I relaxed my density threshold a little bit. Okay. Would I then find something maybe that was two-dimensional, that actually, then sort of contained more information somehow? Okay. So this is what happens when you do this. So if you look at this, now I need to keep track of the Betti 2 as well. You can see Betti naught equals 1. That's a single long line. That's very consistent. Betti 1 equals 2. Well, you can see there are really two long lines. There's a lot of small stuff happening as it arranges itself in here. But for a long time, there's actually two bars there. And then Betti 2 equals 1. You might argue with me a little bit about that there's a small bar underneath that long two-dimensional bar there, but it's not very long. So we're going to ignore it, and we're going to say, and believe, that whatever this is, its homology should be, have a configuration 1, 2, and 1. Now, let me recall back at the very beginning when I showed you the Klein Bottle. Remember that its mod 2 Betti numbers are also 1, 2, and 1. Okay? But if we think of the classification of surfaces, that doesn't quite pin it down because there's another one that has the configuration 1, 2, and 1, which is the torus, exactly. Okay? Now, so can you tell the difference between those two? How can you tell which one is occurring? Well, we're doing mod 2 homology here. It's not hard to check that if you do mod 3 homology for a Klein Bottle versus mod 3 homology of a torus, you will get different answers. And so it turns out that when you perform that calculation, and you can do exactly that mod 3 calculation here too, that it pins it down and says that indeed it is a Klein Bottle. Okay? So the homology of the space that we get is the homology of a Klein Bottle. And the question now is, just like before we were trying to explain the presence of these loops, can we somehow explain this Klein Bottle as working with this? Now, of course, the picture that I showed you of the Klein Bottle, pretty as it is not something that one can work with computationally or in any other way. You can look at it, but you can't do much else with it. But of course, we have the identification space model that you're all familiar with, which glues things together with a twist in the vertical direction and without a twist in the horizontal direction. Okay, so this is a way that one can work with the Klein Bottle, just as a rectangle where you remember that there are some identifications that are made. And so the question now is, well, what about the three-circle model, now which we've built? Does it fit somehow naturally into this Klein Bottle? Well, here's the primary circle, and I've recolored it to red here. You'll notice that is a circle, right, because the P is glued to the P and the Q is glued to the Q. Okay. And now let's do this. Let's put in the secondary circles. So the secondary circles, these are both circles also because R is glued to R and S is glued to S. And furthermore, each of these secondary circles intersects the primary one twice, and they don't touch each other. So it's a perfect embedding of the three-circle model in the Klein Bottle. And so now what you can do is you can actually fill it out and see how the Klein Bottle parametrizes those patches. So I've made them round here just because of my own issues with Illustrator. But what you can see here is this node, this one right here is the same as the one with the twist up there. This one right here is the same as that one, and so forth. Okay. So, so it does fit, and in fact, this is the explanation then for, if you like, what the frequently occurring motifs among high variance 3x3 patches in in natural images. Now, there are a couple of things I'd like to say about this. So one is sort of mathematical and one is scientific. Let's look at the mathematics first of all. So we've done sort of a discretized calculation. Now, here's what one could call a Platonic answer, or the Platonic explanation for this. So let's now suppose instead we don't just have the 3x3 patch. We've actually got the full intensity function on a rectangle. So its intensity is just the dark, light to dark. And let's suppose that we consider just quadratic polynomials in two variables. Okay? There are actually 6 parameters pinning down such a polynomial: 1 constant, 2 linear, and 3 quadratic terms. Okay? But now remember, we did some things to these patches. First of all, we mean-centered them. That means we're going to consider only those patches, and in this case only those functions, whose mean value across the rectangle, or the square, is 0. So that's that condition 3 there. Then secondly, we actually made the L2 norm be equal to 1 as well. And so we can do that here as well and consider a function whose integral of f squared is equal to 0. Now, the effect of that has been we started from a 6-dimensional vector space. The first linear condition moved us down to a 5-dimensional vector space. And now we put ourselves on a sphere in that vector space. We're now on a 4-sphere. Okay? So there's got to be some additional condition. And the condition is a nonlinear one. The condition is the one that says that your quadratic function can be composed as single variable quadratic composed with a linear term. A simple linear term. And when you do that, you find that that cuts down the dimension by 2. You get a codimension 2 subspace sitting inside the 4-sphere. And it's a fun exercise to check that it's homeomorphic to a Klein bottle. Okay? So it suggests, first of all, a way of thinking about it, thinking about the problem in a more idealized way. The second and final point I wanted to make about this is that the original motivation for the Dutch guys who drove around Groningen taking pictures, they wanted to say, can we say anything about the relationship between the statistics of what's coming into natural images and the way that the primary visual cortex works. So the primary visual cortex, sometimes called V1, is an early stage part of the visual pathway. It does low-level analysis of local stuff going through. And it was studied quite intensively by Hubel and Wiesel in the 60s, I believe, maybe even 50s. And so the question is, how does it work? How are these neurons, what happens with the neurons? And so what they found is that there's neurons that are tuned to capture certain specific things. So, for example, there's a neuron that's tuned to, there's a neuron that's tuned to capture this primary circle one, or this one. So it will fire only if it sees a linear gradient of a given angle. Okay? That's when it fires. Okay? Now, why is it doing that? Let's think for a second. If you're trying to encode something coming in, and you know that some things happen more frequently than others, what you would want to do is you would want to encode those things that happen really frequently. You would want to encode those with few bits if you're trying to compress and make things efficient. That's a general principle, it's an important engineering principle in building compression. And the human system is also interested in doing compression so as to get maximum bang for your buck here in recognizing things. Okay? So the idea that it would take a single neuron and tune it to this is perhaps motivated by the fact that this is something that happens frequently. What is really interesting, though, is that what Hubel and Wiesel also found is that not only are there things tuned to these guys, there are also things tuned to these guys. So there are things which will not fire when you see a linear gradient, but which will fire when you see a line in the middle of a region. So again, it is seeing that is recognizing that that's a frequently occurring motif, and so it is expending a whole neuron to capture it. Okay, so we'll look a bit more at some other applications and then start talking about there's some more theoretical aspects of this whole idea of persistence. The point of this lecture was to show that it is something that genuinely works. All right, thank you.